Somewhere beyond Neptune, 5 to 10 times the mass of Earth, a planet has been orbiting our Sun for 4.5 billion years without us knowing it was there. Tonight we map the evidence, the search, and the physics of why something so large can be completely invisible. This is not a story about a distant, speculative possibility that might or might not be real. It is a story about a gravitational fingerprint that has been measured in multiple independent datasets, confirmed by multiple independent research groups using different methods, and that points consistently toward a single conclusion: something large is out there, in the darkness beyond Neptune, pulling on the smaller objects of the outer solar system in patterns that we can measure and model with precision. It is also a story about the limits of astronomy, about what the universe can hide from us, and how, and why something 5 to 10 times the mass of Earth, which sounds enormous, which is enormous by every human standard and by most astronomical standards, can evade detection by every telescope on Earth and in space for years after we became confident it was there. The planet has been given a working name, Planet 9, not because we are certain it is the 9th planet in our solar system, a category that has had a complicated history since Pluto's reclassification in 2006, but because 9 is what the number will be if the planet is confirmed, and because the name is specific enough to attach to the hypothesis and the search. Planet 9, if it exists, would be the most significant discovery in planetary astronomy in more than 160 years. Neptune was discovered in 1846, predicted from anomalies in Uranus's orbit, and found within 1 degree of where the prediction said it would be. Planet 9, if confirmed, would follow the same pattern, discovered from gravitational evidence before direct optical detection. Its position triangulated from the orbits of smaller objects it has been silently shepherding for billions of years. The difference is that the prediction for Neptune was made and confirmed within months. The prediction for Planet 9 has been standing since 2016, and the planet has not yet been directly observed. That gap between prediction and confirmation is the heart of this story. It is a gap created not by uncertainty in the evidence, which is strong, but by the physics of what it means to be very large, very cold, and very far away. And it is a gap that may close in the next few years as a new telescope comes online that was specifically designed to find exactly this kind of object. The planet we are looking for is not a hypothetical ghost, it is a gravitational fact. The same kind of gravitational fact that led astronomers to Neptune in 1846, when Uranus was observed to deviate from its predicted orbit, and the only reasonable explanation was the gravitational influence of an unknown body beyond it. Urbain Le Verrier did the calculations, Johann Galia pointed the telescope, and Neptune was where the math said it would be. The pattern here is the same. Not the orbit of a known planet deviating from prediction, but the orbits of a dozen small worlds in the outer solar system, aligned in a configuration that should not exist if the only gravitational forces acting on them come from the known planets. The math points to something. The telescopes have not yet confirmed it, but the math is precise and the telescopes are getting better. To understand why Planet 9's existence would be so significant, it helps to understand what it would mean for the census of our solar system and for the models of how solar systems form. Our solar system has, as far as we currently know, 4 terrestrial planets, 4 giant planets, and a vast assortment of smaller bodies, asteroids, comets, Kuiper belt objects, Oort cloud bodies. The terrestrial planets are small and rocky. The giant planets divide into 2 pairs: Jupiter and Saturn, the gas giants, made primarily of hydrogen and helium, and Uranus and Neptune, the ice giants, made of water, ammonia, and methane ices with thin hydrogen-helium envelopes. What our solar system conspicuously lacks is any planet between Earth's mass and Neptune's mass in the range 1 to 17 Earth masses. This gap is peculiar because planets in exactly this mass range, called super-Earths or mini-Neptunes, are the most common type of planet found orbiting other stars. Surveys of exoplanetary systems consistently find that stars with planets are more likely to have a planet in the 1 to 10 Earth mass range than in any other category. The solar system appears anomalous in not having one. Planet 9, at 5 to 10 Earth masses, would fill this gap. It would mean that the solar system does have a super-Earth, just not where we expected it, not in the habitable zone of the Sun where water can be liquid, but in the cold outer darkness where it has been sitting, undetected, for 4.5 billion years. This matters for planetary science in 2 directions at once. In one direction, it suggests our solar system is more typical than it appears, that we do have the most common type of planet, we just have not found it yet. In the other direction, it raises the question of why our super-Earth is in such an unusual location. Most super-Earths orbit their stars at distances of less than 1 astronomical unit, far closer than even Mercury orbits our Sun. Planet 9, at 400 to 800 astronomical units, is hundreds of times farther from the Sun than most known super-Earths are from their host stars. Explaining how it got there, and why it is so far out while other solar system super-Earths are so close in, is a different but equally interesting puzzle. The discovery, when it comes, will not simply add a name to the list of solar system planets. It will reopen questions that planetary scientists thought they had partially answered, and force a more careful examination of what is typical and what is unusual about the solar system we live in. If this is the kind of mission briefing you want more of, subscribe and stay with the crew. Strap in. We begin. But first, the anomaly. Because everything about Planet 9 begins with something that should not be there, in data that was not collected to find it, spotted by researchers who were looking for something else entirely. The story of Sedna deserves slightly more attention than it usually receives, because Sedna itself is a remarkable object that challenged planetary scientists even before Planet 9 was proposed. When Mike Brown discovered Sedna in 2003, the immediate reaction was a combination of excitement and puzzlement. The puzzlement was genuine and deep. Sedna's perihelion distance of 76 astronomical units placed it entirely outside Neptune's gravitational sphere of influence. Neptune's gravity can substantially affect objects with perihelion distances out to roughly 40 to 50 astronomical units. Objects beyond that distance, moving on orbits that never bring them close to Neptune, cannot have had their orbits shaped by Neptune's gravitational influence in any direct way. This creates a problem. How did Sedna get its current orbit? Every object in the solar system started in roughly the same region of the protoplanetary disk, the flat disk of gas and dust that surrounded the young Sun. Objects in the outer disk, beyond Neptune, would have formed in the Kuiper belt region, or slightly beyond it. Their initial orbits would have been nearly circular and roughly coplanar with the ecliptic. To end up in an orbit like Sedna's, highly eccentric and with a perihelion far beyond Neptune's reach, something would have had to perturb it. 3 mechanisms were proposed for Sedna's origin. First, a close encounter with a passing star during the Sun's early life in its birth cluster could have pulled Sedna outward into its current orbit. Second, the gravitational effect of the protoplanetary disk itself, before the disk dispersed, could have shaped orbits at large distances. Third, a distant massive planet, shepherding Sedna much as Planet 9 is now proposed to shepherd the extreme trans-Neptunian objects, could have placed Sedna in its current orbit billions of years ago. None of these mechanisms was clearly favoured based on Sedna alone. A single data point is not a discriminating test, but Sedna established something important. Objects in genuinely anomalous orbits exist in the outer solar system, and the standard model of solar system formation does not naturally produce them. The outer solar system is not the simple, well-understood place that models suggested. The discovery of 2012 VP113 a decade later doubled the anomaly, and when Battigen and Brown examined the full population of extreme trans-Neptunian objects systematically, the anomaly multiplied. There is a specific aspect of the TNO clustering that is more compelling than the argument of perihelion clustering alone, the clustering of the orbital pole direction. The orbital pole of a solar system object is the direction perpendicular to its orbital plane. For the planets, these poles are all roughly aligned with the Sun's rotation axis, a consequence of the common origin in the protoplanetary disk. But the extreme trans-Neptunian objects, if they were distributed randomly, should have poles pointing in all directions with equal probability. They are not randomly distributed. The orbital poles of the extreme TNOs cluster in a specific direction, tilted roughly perpendicular to the direction of the clustering in their perihelion positions. This is exactly what you would expect from a massive distant planet in a specific orbital plane. The planet's gravity would preferentially align the orbital poles of smaller bodies it interacts with. The clustering in 2 independent orbital parameters, the argument of perihelion and the orbital pole direction, is much more statistically significant than the clustering in either parameter alone. 2 independent alignments, both consistent with the same proposed planet configuration, represent much stronger evidence than one alignment would. Brown and Battigan calculated the probability that both alignments occurred by chance as approximately 0.007%. Later analyses by other groups have found somewhat different numbers depending on which TNOs they include and how they model the observational bias, but even the most conservative estimates find probabilities in the range of a few percent, which is still a significant anomaly in a system with only a handful of known extreme TNOs. If you add more extreme TNOs to the sample, the probability of a random chance alignment decreases rapidly. The prediction is clear: as more extreme trans-Neptunian objects are discovered, if they continue to show the same clustering pattern, the statistical case for Planet 9 will grow stronger with each new discovery. If the clustering dissolves as new objects are found in non-aligned orientations, the case will weaken. In the years since 2016, the new extreme TNOs discovered have predominantly continued to show the clustering pattern. The statistical case has strengthened, not dissolved. The story begins with Sedna. In November 2003, Mike Brown, a planetary astronomer at Caltech, and his collaborators discovered a small world at the outer edge of the solar system. They named it Sedna, after the Inuit goddess of the sea. Sedna was unusual in almost every way that matters for the orbit of a solar system object. Most objects in the outer solar system follow predictable rules. They either orbit at distances where Neptune's gravity can affect them, or they exist in the distant Oort cloud, a vast spherical shell of comets extending tens of thousands of astronomical units from the Sun. But Sedna sat in neither of these regions. Its closest approach to the Sun, called its perihelion, was at 76 astronomical units, well beyond Neptune's gravitational reach. Its farthest point, its aphelion, was estimated at roughly 1,000 astronomical units. It took about 11,400 years to complete one orbit. Nothing in the standard model of solar system formation predicted an object in Sedna's orbit. Neptune's gravity cannot reach it. The Oort cloud's objects are typically perturbed inward by passing stars or the gravitational tide of the galaxy. Sedna was not being perturbed in any obvious way. It was simply there, following an enormous elliptical orbit that had no clear explanation within the models astronomers had spent decades developing. Mike Brown said at the time that Sedna was the most distant object ever observed in the solar system, and that its orbit made no sense. He meant both of those things literally. For a decade after Sedna's discovery, it was the only object of its type, a curiosity, a single anomalous data point, which in astronomy usually means either a genuine discovery or an error in observation. In this case, it was the former, but a single data point is not a pattern. Then, in 2012, another object was discovered. This one was found by Scott Shepard of the Carnegie Institution for Science and Chad Trujillo of Gemini Observatory. They named it 2012 VP113, and like Sedna, it sat in a region of the solar system with no good explanation for how it got there. Its perihelion was at 80 astronomical units. Its orbital period was estimated at roughly 4,000 years. Its orbit was strange in the same way that Sedna's was strange. Two objects in strange orbits are a pattern, or at least the beginning of one. Shepard and Trujillo looked at the two objects together and noticed something. Sedna and 2012 VP113, along with several other extreme trans-Neptunian objects, shared a peculiar alignment. Their orbits were not random. Specifically, a parameter called the argument of perihelion, which describes the orientation of an orbit in space, was clustered near 0 degrees for most of the known extreme trans-Neptunian objects. The argument of perihelion tells you where in an orbit an object is at its closest approach to the Sun. If this value is random, you would expect it to be distributed uniformly across all angles from 0 to 360 degrees. It was not, it was clustered. Most of the extreme objects, the ones with orbits far beyond Neptune's influence, had their closest approaches oriented in roughly the same direction. Shepard and Trujillo published this finding in 2014 and suggested that it might indicate the presence of a distant massive planet that was shepherding the smaller objects into this preferred orientation. They did not pursue the detailed calculation of what that planet would need to be. Mike Brown and his Caltech colleague Konstantin Batygin took the suggestion seriously. They spent months running calculations, checking observational biases, testing alternative explanations, and in January 2016 they published a paper in the Astronomical Journal that changed the conversation. Their analysis went significantly beyond the argument of perihelion clustering. They examined a cluster of 6 extreme trans-Neptunian objects, all with semi-major axes greater than 250 astronomical units, and perihelion distances greater than 30 astronomical units. These objects shared not just one orbital parameter, but several. Their perihelia were clustered in physical space, meaning they were all making their closest approaches to the Sun in roughly the same part of the sky. Their orbital planes were all tilted in similar ways relative to the plane of the solar system. The clustering was not in one dimension, but in 3. Brown and Battigan calculated the probability that this clustering was a random coincidence. They arrived at approximately 0.007%, roughly 1 chance in 14,000 that the arrangement occurred by chance. That is not the kind of number you dismiss. But statistics are only as good as the data they are applied to, and the data on extreme trans-Neptunian objects is subject to a significant observational bias. We find these objects when they are near their perihelia, because that is when they are closest to the Sun and brightest. If our surveys have covered only certain parts of the sky, the objects we have found will cluster in those parts of the sky, regardless of any genuine physical clustering. The statistical significance of the clustering could be an artifact of where we have and have not looked. Brown and Battigan addressed this objection carefully. The surveys that discovered the extreme trans-Neptunian objects were conducted in different parts of the sky at different times. If the clustering were purely a sampling artifact, you would expect it to reflect the geometry of the surveys rather than a coherent physical orientation. Instead, the clustering was consistent across surveys conducted at different times, with different instruments in different parts of the sky. The surveys covered enough of the sky that a randomly distributed population of objects would have shown the sampling pattern rather than the physical clustering. They also ran simulations of what happens when you remove the clustering and assume a uniform distribution. The expected number of observed objects clustering in the way the data shows, given the survey coverage, was inconsistent with the hypothesis of no clustering. The physical clustering was real. What physical mechanism could produce it? The mechanism Brown and Battigan proposed is elegant. A massive planet on a distant eccentric orbit, with its perihelion on the opposite side of the Sun from the cluster of extreme trans-Neptunian objects, would gravitationally shepherd those objects into specific orbital orientations through a resonance mechanism. Objects that spend time near the planet's orbit get gravitationally nudged. Over billions of years, this nudging preferentially removes objects from certain orbital orientations and preserves others. The result is a cluster of objects whose orbital orientations are opposite to the planet's perihelion. This is not a novel mechanism. Similar shepherd planet effects have been proposed and confirmed elsewhere in the solar system. Neptune itself shepherds the Kuiper belt objects in resonant orbits. The mechanics are well understood. The question is whether the evidence in the extreme trans-Neptunian object population is strong enough to justify the conclusion that a large planet is responsible. The evidence grew stronger as more objects were discovered. By 2020, the number of extreme trans-Neptunian objects with the relevant orbital characteristics had grown to approximately 20. The clustering persisted. New objects continued to appear in the predicted orientations. Objects with orbital orientations inconsistent with the Planet 9 hypothesis were either not found or found at rates consistent with the model's predictions. The anti-clustering argument, proposed by Corey Shankman and others, suggested that the bias in the survey coverage was larger than Brown and Battigan acknowledged. This debate remains ongoing in the scientific community, but subsequent analyses using improved bias corrections have generally found that the clustering cannot be entirely explained by survey bias. Something is doing the clustering. There is a specific object that deserves more attention before we leave the anomaly section, because it illustrates more clearly than any other why the Planet 9 hypothesis was taken seriously rather than dismissed. Sedna is not just unusual in its perihelion distance. It is unusual in a specific way that rules out most conventional explanations. An object can end up far from the Sun with a large perihelion distance through several mechanisms. Neptune can scatter an object outward to very large semi-major axes while keeping the perihelion near Neptune's orbit. Galactic tides can lift the perihelion of an Oort cloud object inward during a passage through the galactic plane. A passing star can perturb a distant object's orbit during a close encounter. But none of these mechanisms explain Sedna's specific orbit simultaneously. Sedna's perihelion is too large for Neptune scattering, which would require the perihelion to be near Neptune at some point in the object's history. Galactic tides work at distances of thousands of astronomical units, far beyond Sedna's semi-major axis of about 500 astronomical units. Passing star encounters are too rare in the current stellar environment to be likely for Sedna specifically, and even if they occurred, they would tend to produce very eccentric orbits that differ from what is observed. The combination of a moderate semi-major axis and a large perihelion distance, with no close encounters with any known perturber possible, defines a specific dynamical problem that Sedna poses. Brown pointed this out in 2003 and proposed that Sedna might have been captured or perturbed during the Sun's early cluster life, when stellar encounters were frequent and could have placed Sedna in its current orbit. This was a reasonable suggestion, but it left open the question of why Sedna's orbit is special and whether other objects shared its particular dynamical niche. The discovery of 2012 VP113 changed the question from why does Sedna exist to why do objects like Sedna exist. The existence of a second object with similar orbital properties suggested that the mechanism was not a rare fluke affecting a single body, but something that had operated on a population of objects. And a mechanism that operates on a population of objects is more likely to be an ongoing gravitational influence, such as a distant massive planet, than a one-time event such as a specific stellar encounter. The subsequent discovery of additional extreme trans-Neptunian objects, each with large perihelion distances and large semi-major axes, all sharing the clustering of orbital orientations, transformed the question again. Not, why do objects like Sedna exist? But why do they all point the same way? That question has a clean answer if there is a massive planet in the outer solar system. It does not have a comparably clean answer from any of the alternatives that have been proposed. The clustering is the key evidence, not the existence of any individual extreme TNO, but the specific orientation shared by all of them. The physics of gravitational shepherding predicts exactly this kind of orientation clustering. No other mechanism currently proposed predicts it with comparable specificity. This is the structure of the argument. Not we see an anomalous object, therefore there must be a planet, but we see a specific population of objects all oriented in the same way, and the most parsimonious explanation for that specific orientation is a planet in a specific location causing it. The specificity of the prediction and the prediction's success in pointing toward a consistent set of orbital parameters for the supposed planet is what makes the argument strong. It is not proof. It is a very good hypothesis, and very good hypotheses deserve to be tested seriously. The anomaly is real. The question is what caused it, and the answer that best fits the data is a planet. Now the question becomes, if there is a large planet in the outer solar system, why have we not found it directly? There is another aspect of Planet 9's invisibility that is worth examining in detail, because it illustrates a general principle about the limits of astronomical surveys. When astronomers conduct sky surveys looking for faint moving objects, they are essentially looking for needles in a haystack where both the needles and the hay are moving. Every image contains millions of point sources, stars, galaxies, and potentially solar system objects. The solar system objects are distinguished from background stars by their motion. They move against the fixed background of stars from image to image. Finding them requires comparing images taken at different times and identifying point sources that have changed position. For objects in the inner solar system, asteroids and comets within a few astronomical units of the Sun, this motion is easily detectable in images separated by hours or a single night. Such objects move several arcseconds per hour, far enough to identify their motion in a single night of observations. Finding them is a matter of having a wide enough field of view, a deep enough sensitivity, and a fast enough cadence to catch them in motion. For objects in the middle solar system, Kuiper belt objects and centaurs at tens of astronomical units, the motion is slower, arcseconds per day to arc minutes per year, still detectable in images separated by days to months, but requiring more careful analysis and longer time baselines. For Planet 9, at several hundred astronomical units, the motion is arcseconds per year. In a single night, the planet moves by a fraction of an arcsecond, far less than the resolution of ground-based telescopes blurred by atmospheric seeing. In a month it moves by a few tenths of an arcsecond, still smaller than the typical seeing limit. In a year it moves by a few arcseconds, just barely detectable with precise astrometry. This means that every standard moving object detection algorithm every pipeline designed to find asteroids and comets from comparison of images taken hours or days apart will completely miss Planet 9. The planet will appear as a stationary faint star in any comparison of images taken less than a month apart. Even in images a month apart, the motion will be comparable to the astrometric uncertainties in typical survey data. Detecting Planet 9 requires a specific type of search strategy, comparing images taken 6 to 12 months apart and looking for very slight motion in faint sources. This requires storing high-quality astrometric data over long-time baselines, precisely calibrating the positions of all faint sources across multiple epochs, and running detection algorithms designed specifically for very slowly moving objects. This is not impossible, but it is significantly more computationally intensive and time-consuming than standard moving object detection. Until very recently, no survey had been specifically designed and optimized for this regime. The other dimension of invisibility that deserves attention is the wavelength problem. Planet 9, at 40 Kelvin, emits almost all of its thermal radiation at wavelengths between 50 and 200 micrometers. This is the far infrared. Ground-based telescopes are essentially blind in the far infrared because water vapor in Earth's atmosphere absorbs radiation at these wavelengths before it reaches the telescope mirror. Observing at far infrared wavelengths from the ground requires being at very high, very dry sites, and even then only certain narrow atmospheric windows are accessible. Space telescopes can observe at far infrared wavelengths without atmospheric interference. The Spitzer Space Telescope, Herschel Space Observatory and others have conducted important surveys in the mid and far infrared. But these missions had limited fields of view and did not complete surveys of the full sky to the depth required to detect an object at Planet 9's distance. The WISE and NEOWISE missions conducted all-sky surveys in the mid-infrared at wavelengths of 3 to 22 micrometers. This range is somewhat short of the peak emission wavelength of a 40 Kelvin object, which falls around 70 micrometers. At 22 micrometers, a 40 Kelvin object emits only a fraction of its total radiation, and the WISE sensitivity at that wavelength is not sufficient to detect a Planet 9 mass object at 600 astronomical units, unless the object is significantly warmer than equilibrium temperature suggests, or has unusual emissivity properties. Future space missions dedicated to far-infrared astronomy could in principle detect Planet 9 thermally, even if it evades optical detection. But no such mission is currently in development with the combination of angular resolution and survey speed required to conduct a full-sky search at the relevant sensitivity. For now, the most promising detection strategy remains optical, using reflected sunlight, requiring the combination of depth and wide-field coverage and slow-moving object detection algorithms that the Vera Rubin Observatory is specifically designed to provide. The answer is a lesson in the physics of cold, distant objects, and it is more complete an answer than most discussions of Planet 9 provide, because the invisibility of the planet is not just a matter of being far away. It is a matter of the specific ways in which distance and temperature interact to make an object essentially transparent to every instrument we have currently deployed. Start with the most basic fact. Planet 9, if it exists at the parameters suggested by the TNO clustering, is between 400 and 800 astronomical units from the Sun. The best current estimate from the modelling centres, around 500 to 600 astronomical units. Let us use 600 astronomical units as our working distance. At 600 astronomical units, the planet receives sunlight at an intensity 360,000 times weaker than Earth does. This number is the square of the distance ratio. 600 squared is 360,000. The inverse square law of light propagation reduces the intensity of any radiation by the square of the distance from the source. This makes Planet 9 receive very little energy from the Sun. Very little energy means very little reflected light, and very little reflected light means it is very dim in the optical wavelengths where most telescopes operate. But there is a further complication, specific to reflected light from solar system objects. The amount of reflected light that reaches Earth is not just a function of how much light reaches the planet. It is a function of how much light reaches the planet multiplied by how much of that reflected light travels the distance from the planet to Earth. The planet at 600 astronomical units reflects light toward Earth, and that reflected light then has to travel approximately 600 astronomical units to reach us. The intensity of reflected light falls off as the square of both the source to object distance and the object to observer distance. For a planet at 600 astronomical units, the total reduction in reflected light compared to what we would see if the planet were at Earth's distance is roughly proportional to 600 to the fourth power divided by a correction for the geometry. 600 to the fourth power is roughly 1.3 times 10 to the 10th. Planet 9, as a reflective object, is roughly 13 billion times fainter than it would be at 1 astronomical unit from both the Sun and Earth. This produces an expected apparent magnitude for Planet 9 in the optical range of roughly 22 to 25, depending on the planet's size, albedo, and current distance from the Sun. At magnitude 25, Planet 9 would be visible with a long exposure image through a large telescope. It is not below the absolute threshold of optical astronomy. It is just very, very faint and very slow moving. But there is a second issue: thermal radiation. An object in the outer solar system is not just reflecting sunlight, it is also emitting its own thermal radiation. Every object with a temperature above absolute zero emits electromagnetic radiation. The wavelength of peak emission is determined by the object's temperature according to a relationship called Wien's displacement law. At room temperature, around 300 Kelvin, the peak emission is in the infrared. At the surface temperature of the Sun, around 5,800 Kelvin, the peak is in visible light. At 600 astronomical units from the Sun, receiving only 1/360,000th of the solar flux that Earth receives, Planet 9 would achieve a thermal equilibrium temperature of roughly 35 to 45 Kelvin. That is about -228 to -233 degrees Celsius, just a few dozen degrees above absolute zero. At 40 Kelvin, an object's thermal emission peaks at a wavelength of roughly 72 micrometers. This is deep in the far infrared part of the electromagnetic spectrum, well beyond the wavelength range of most ground-based telescopes, which are limited by water vapor in the atmosphere that absorbs far infrared radiation. Space telescopes like the Herschel Space Observatory have surveyed the sky in the far infrared, but their coverage was incomplete, and their sensitivity, while impressive, was not sufficient to detect a planet of Planet 9's expected properties at 600 astronomical units. The Wide-Field Infrared Survey Explorer, WISE, and its successor, NEO-WISE, have conducted all sky surveys in the mid-infrared. WISE could in principle detect a planet-sized object in the outer solar system. After the Planet 9 hypothesis was announced, Brown and Batajian checked the WISE data carefully. They found no clear detection. This does not rule out Planet 9, because the mid-infrared sensitivity of WISE at 600 astronomical units is marginal for an object of the expected size and temperature. The planet, if it exists, may simply be below the WISE detection threshold. There is another factor that makes Planet 9 hard to find, even in surveys with sufficient sensitivity. It is moving extremely slowly. Most solar system object detection works by comparing images taken at different times and looking for objects that move against the background of fixed stars. Asteroids and comets move noticeably against the background in images separated by hours or days. Outer solar system objects like Pluto move perceptibly over days to weeks. But Planet 9, orbiting the Sun at 600 astronomical units, completes one orbit every 10,000 to 20,000 years. In 1 year, it moves perhaps a few arcseconds across the sky. In one night, it moves perhaps 1/100th of an arcsecond. This is such slow motion that in any individual image or pair of images separated by days, Planet 9 would be essentially indistinguishable from a faint background star. You need images separated by months to years to identify Planet 9's motion above the precision of the astrometric measurement, and during that interval, you need to confirm that the object is still there in each image, which means covering the same part of the sky repeatedly with the same depth of survey. No current sky survey has been optimized for this combination of requirements. The surveys that go deep enough to detect Planet 9 typically cover a limited area and do not return to the same area frequently enough to detect slow-moving objects. The surveys that cover the sky rapidly and repeatedly, like the Catalina Sky Survey and the Palomar Transient Factory, are not deep enough to detect Planet 9 at its expected magnitude. There is a further complication related to where in the sky Planet 9 might be. The current constraints on Planet 9's orbital parameters suggest that it is most likely to be found in a broad swath of sky that spans from roughly right ascension 2 hours to 8 hours. This region corresponds to a part of the sky that includes significant portions of the Milky Way's galactic plane, where background star density is high. Against a dense field of background stars, finding a faint moving object requires very high-quality astrometry and careful background subtraction. The galactic plane crowding makes the search harder. Additionally, if Planet 9 is on a highly eccentric orbit and is currently near its aphelion, its farthest point from the Sun, it would be both farther away and moving more slowly than if it were near perihelion. Near aphelion, it would be at maximum distance, maximum faintness, and minimum apparent motion. The probability that Planet 9 is currently near aphelion is not negligible. A planet with an orbital period of 15,000 years and an eccentricity of 0.4 spends most of its time near aphelion, because it moves most slowly there. The probability of finding it near perihelion at any given moment is relatively small. So we have a convergence of unfavourable factors, an expected apparent magnitude of 22 to 25 near the edge of deep survey capability, a thermal emission in the far infrared where ground-based astronomy is limited and space-based surveys have marginal sensitivity, an apparent motion too slow to be easily identified in standard moving object search algorithms, a location possibly in or near the galactic plane where background crowding is a challenge, and a possible location near aphelion where all of these problems are at their worst. The invisibility of Planet 9 is not a mystery. It is the expected consequence of the physics. The planet is behaving exactly as a large, cold, distant object should behave. We simply do not yet have the instruments required to find it in the part of the sky where it probably lives, at the depth required to detect it, with the cadence required to identify its slow motion. There is a thought experiment that makes the detection difficulty vivid, in a way that technical descriptions sometimes fail to convey. Imagine you're standing in a dark parking lot, looking for a marble that has been dropped somewhere in the lot. The marble is painted black. The parking lot is lit only by starlight. You have a flashlight, but the batteries are weak and the beam is narrow. The marble could be anywhere in the lot and you have to sweep the entire area to find it. Now imagine the parking lot is the size of Texas. That is roughly the situation astronomers are in when looking for Planet 9. The planet is out there somewhere in a broad swath of sky, spanning perhaps 15 to 20% of the full celestial sphere. The planet reflects very little light and emits its thermal radiation at wavelengths where our telescopes are least sensitive. The planet moves so slowly that it looks like a background star in any individual image, and the region of sky most likely to contain it overlaps with the densest part of the background star field, the galactic plane, where distinguishing a faint point source from the thousands of other faint point sources in the same image is a genuine challenge. Each of these difficulties is solvable in principle, but they all need to be solved simultaneously, with a single telescope system that has the right combination of mirror size, camera field of view, image quality, spectral coverage, and observation cadence. That combination does not exist in any current facility. It is being built now. The Vera Rubin Observatory's combination of an 8.4-meter mirror with a 9.6 square degree field of view and a survey cadence that returns to each sky position every few nights is specifically designed to address these combined requirements. The mirror is large enough to detect objects at Planet 9's expected magnitude. The field of view is wide enough to survey the predicted search region rapidly. The cadence is frequent enough to accumulate deep co-added images that go even fainter than individual visits. The specific technical challenge of slow-moving object detection is being addressed through dedicated software development. The Rubin Observatory's data processing infrastructure includes a specialized pipeline component called the Solar System Processing Pipeline, which uses the accumulated multi-epoch imaging data to search for moving objects across a wide range of apparent motion rates, from fast-moving near-Earth asteroids to very slowly moving trans-Neptunian objects like the expected Planet 9. This pipeline uses a technique called shift and stack, in which images are shifted by amounts corresponding to the expected motion of a solar system object at a given distance, and then stacked to increase the signal-to-noise ratio. A real object moving at a consistent rate across all the images will add coherently when the stack is aligned correctly, revealing itself above the noise. A background star or galaxy will be smeared out when the images are shifted and will not add coherently. For Planet 9, the shift and stack technique requires shifting images by approximately 0.01 to 0.05 arcseconds per night, corresponding to the expected range of apparent motion at the predicted distance. Running this search across the full Rubin survey area Testing all possible motion vectors in the range expected for Planet 9 requires significant computational resources, but the Rubin Observatory's data management system is designed for exactly this kind of computationally intensive analysis. The expected result of the shift and stack search, if Planet 9 is in the survey area and at the predicted brightness, is a statistical signal above the noise after stacking 3 to 12 months of Rubin images of the same region. The signal would be a faint point source that appears when the images are shifted at the correct rate and disappears when shifted at incorrect rates. Follow-up observations would then confirm the object and measure its orbit. This is not speculation about future capabilities. It is a description of a planned analysis that will be run on Rubin data as a matter of standard procedure. The algorithms are being developed and tested now. The question is not whether the search will be conducted. It will be. The question is what it will find. That is going to change. The orbital constraints on Planet 9 have been refined significantly in the years since the original 2016 paper, and some of the refinements are worth examining because they tell a more precise story about what we are looking for and where. In 2019, a team led by Konstantin Batygin and collaborators published a revised analysis that incorporated all of the then-known extreme trans-Neptunian objects with sufficient orbital determination. The revised analysis found that the clustering was more significant than the original 2016 paper suggested when additional TNOs were included, and it refined the orbital parameter estimates for Planet 9. The revised best estimates were semi-major axis between 400 and 800 astronomical units, with the median around 500 astronomical units, eccentricity between 0.2 and 0.6, with the median around 0.35, inclination between 15 and 30 degrees, and mass between 5 and 10 Earth masses. These parameters imply an orbital period between roughly 7,500 and 25,000 years, with the median near 10,000 years. Planet 9, if it has been in roughly its current orbit for most of the solar system's history, has completed somewhere between 180,000 and 600,000 orbits since the solar system formed. Each orbit has taken between 7,500 and 25,000 years. The inclination of the orbit is particularly interesting. If Planet 9 is inclined by roughly 20 degrees to the ecliptic, its orbital plane is significantly tilted relative to the plane of the other planets. This is unusual. The planets in the inner and outer solar system all orbit within about 7 degrees of the ecliptic. An object tilted by 20 degrees is dynamically distinct from the other planets. This inclination is actually predicted by the Planet 9 mechanism. To produce the specific mix of orbital tilts observed in the extreme trans-Neptunian objects, including both objects that are aligned with the ecliptic and objects that are significantly inclined to it, the shepherding planet must itself be inclined. A Planet 9 at zero inclination could not produce the full diversity of TNO inclinations observed. The inclination also has implications for the search. If Planet 9 is inclined by 20 degrees, its current sky position may be significantly north or south of the ecliptic plane. The ecliptic is where most solar system surveys concentrate their efforts because the known planets and most asteroids are near the ecliptic. A survey optimized for the ecliptic would miss Planet 9 if it is currently far from the ecliptic plane. The Rubin Observatory survey covers a broader strip of sky than the ecliptic alone, extending to roughly 30 degrees of latitude above and below the ecliptic. This coverage is sufficient to find Planet 9 even if it is currently near the maximum excursion from the ecliptic permitted by its 20-degree inclination. There is one more constraint worth mentioning: the orientation of the solar system's invariable plane. The invariable plane of the solar system is the plane perpendicular to the total angular momentum vector of all the planets combined. Because Jupiter and Saturn contain most of the angular momentum of the solar system, the invariable plane is primarily determined by their orbits. The invariable plane is tilted by about 1.6 degrees relative to the ecliptic. If Planet 9 has a mass of 5 to 10 Earth masses and an inclination of 20 degrees, its contribution to the total angular momentum of the solar system would be significant. In particular, it would tilt the invariable plane of the combined planetary system by a calculable amount relative to what we observe today. This is a consistency check on the Planet 9 hypothesis. The total angular momentum of a planetary system with Planet 9 must be consistent with the observed orientation of the outer solar system. Batygin and Brown checked this constraint and found it to be satisfied within the uncertainties of the current Planet 9 parameter estimates. The consistency with the angular momentum constraint does not prove Planet 9 exists, but it shows that the hypothesis, taken in its full detail, is self-consistent across multiple independent checks. That is the character of a good hypothesis. What we know about Planet 9's orbit comes entirely from the gravitational signature it leaves in the outer solar system. No direct detection, no image, no thermal emission measurement, just the patterns in smaller objects and the careful mathematical work of inferring what configuration of a single massive body could produce those patterns consistently. The constraints are surprisingly tight for something we have never seen. The semi-major axis of Planet 9's orbit, the average distance from the Sun, is constrained to be between roughly 300 and 900 astronomical units, with the most likely range centered around 400 to 700 astronomical units. The lower limit comes from the fact that a closer planet would produce effects visible in the inner solar system objects and in the precisely measured orbits of the known planets, effects that have not been observed. The upper limit comes from the requirement that the planet be close enough to have a meaningful gravitational effect on the extreme trans-Neptunian objects over the age of the solar system. The eccentricity, which describes how elongated the orbit is constrained to be between about 0.2 and 0.7. A planet with zero eccentricity would be on a circular orbit and would need to be much closer to produce the observed effects. A very high eccentricity would put the planet's perihelion too close to Neptune, where gravitational interactions would disrupt the orbit over the age of the solar system. The most commonly cited estimate is an eccentricity of about 0.3 to 0.5. The inclination, the tilt of the orbit relative to the plane of the solar system, is estimated to be between about 15 and 35 degrees. Planets in the inner solar system orbit very close to the ecliptic plane, the plane in which Earth orbits the Sun. But the extreme trans-Neptunian objects show a warping of their orbital planes that is consistent with a moderately inclined shepherd planet. A planet with no inclination could not produce the full range of orbital anomalies observed in the TNO population. The mass of Planet 9 is estimated at 5 to 10 Earth masses. This makes it what astronomers call a super-Earth or a mini-Neptune, a category of planet that is, ironically, the most common type of planet in the galaxy, as detected around other stars, but that is apparently absent from our solar system, except possibly as Planet 9. The current distribution of confirmed exoplanets shows a striking gap in our solar system. We have planets ranging from Earth to Neptune's 17 Earth masses, but nothing in between. Planet 9, at 5 to 10 Earth masses, would fill this gap. But the most practically useful constraint is the position in the sky. Where is Planet 9 most likely to be right now? The orbital constraints from the TNO clustering combined with n-body simulations of how a Planet 9 with the specified parameters would produce the observed TNO configuration narrow down the likely region of sky significantly. The perihelion of Planet 9, its closest approach to the Sun, is estimated to be roughly opposite the cluster of extreme trans-Neptunian objects in the sky. Since the TNO cluster is in a specific direction, the perihelion is in the opposite direction. The current position of Planet 9 in its orbit depends on where it is between perihelion and aphelion at this moment in history. With an orbital period of 10,000 to 20,000 years, the planet moves slowly enough that its sky position changes by only a small amount per century. Based on the constraints, the most likely current sky position of Planet 9 is in a region spanning roughly from the constellation Cetus in the west to Orion in the east, along the antigalactic center direction. This narrows the search to perhaps 20% of the full sky. This estimate comes with significant uncertainty, and different groups have proposed slightly different most likely positions based on different assumptions about which TNOs are genuinely in the anti-aligned population and which might be there by chance or bias. But the broad region of sky to search is reasonably well constrained. There is an additional constraint that comes from a completely independent dataset. The precise orbital measurement of the spacecraft Cassini, which orbited Saturn from 2004 to 2017. Cassini's orbit around Saturn was tracked with extraordinary precision using radio ranging. The timing of radio signals sent from Earth to Cassini and back measured the spacecraft's distance to centimeter-level accuracy over years of observation. Any unaccounted gravitational perturbation from a distant massive planet would show up as a systematic drift in Cassini's predicted orbit. Researchers including Agnès Fienga and colleagues at the CNRS in France analysed the Cassini ranging data in detail, looking for any signature of a distant planet's gravity. They found no clear detection but were able to place constraints on where Planet 9 could and could not be. Specifically, they found that a Planet 9 at some orbital positions was inconsistent with the Cassini data, placing limits on the range of current sky positions. The Cassini constraint rules out certain regions of the predicted Planet 9 sky position and makes other regions somewhat more likely. Combined with the TNO clustering analysis, the joint constraint narrows the most likely current position of Planet 9 to a region perhaps 15 to 20 degrees wide in the sky, somewhere in the general vicinity of what astronomers would describe as the constellation Gemini, or the border of Orion and Gemini. This does not mean Planet 9 is definitely there. The constraints are probabilistic, not certain. The planet might be in a different part of its orbit than the most probable one. The constraints might shift as more TNOs are discovered and more spacecraft ranging data is analysed. But the constraints give searchers a priority region. If you have limited observing time on a large telescope, this is the part of the sky most worth examining first. Planet 9's orbital period of 10,000 to 20,000 years deserves a moment of reflection that is usually skipped in technical discussions. The solar system is 4.6 billion years old. In that time, the inner planets have completed billions of orbits each. Earth has completed 4.6 billion orbits. Even Pluto, with its 248-year orbit, has completed roughly 18 million orbits. But Planet 9, with its 10,000 to 20,000-year orbit, has completed only about 250,000 to 460,000 orbits in the entire age of the solar system. It is a slow, solitary object, tracing an enormous ellipse through the outer darkness once every 10 to 20 millennia, silently nudging the smaller objects of the outer solar system into their observed configurations through billions of years of patient gravitational influence. The scale of Planet 9's orbit is difficult to feel. At perihelion, it would be roughly 300 astronomical units from the Sun. At aphelion, perhaps 900 astronomical units or more. The difference between perihelion and aphelion is 600 astronomical units. The entire inner solar system from Mercury to Neptune fits in a sphere about 60 astronomical units across. Planet 9 swings through a range of distances 3 times larger than the entire classical solar system in the course of a single orbit. And somewhere along that enormous elliptical path, at this particular moment in the history of the solar system, it is out there, moving, cold, dark, invisible to everything we have pointed at the sky, until now. The Rubin Observatory is not the only instrument in the search. Several other projects have been contributing to the Planet 9 investigation, and will continue to do so even as Vera Rubin becomes the primary instrument. Japan's Subaru telescope, an 8.2-meter optical infrared telescope on Mauna Kea in Hawaii, is equipped with the Hyper-Suprime Cam, one of the largest and most sensitive wide-field cameras in the world. The Hyper-Suprime Cam covers 1.77 square degrees per image, smaller than Rubin's 9.6 square degrees but with excellent image quality and depth. Teams using the Hyper-Suprime Cam have conducted systematic surveys of the predicted Planet 9 search region, reaching depths comparable to or exceeding what Rubin will achieve in individual visits. These Subaru surveys have not found Planet 9, but they have produced important byproducts. The discovery of new extreme trans-Neptunian objects that have been added to the census used to refine the Planet 9 orbital constraints, and strong upper limits on the brightness of any object in the specific region surveyed. The Dark Energy Survey, which operated from 2013 to 2019 using the Dark Energy camera on the Victor Mesblanco 4-meter telescope at the Cerro Tololo Inter-American Observatory in Chile, covered approximately 5,000 square degrees of the southern sky in multiple bands, achieving depths of roughly magnitude 23 to 24. Several teams have analysed the Dark Energy Survey data specifically for Planet 9 candidates and for new extreme trans-Neptunian objects. These analyses have found dozens of new trans-Neptunian objects, but no clear Planet 9 candidate. The non-detection constrains the current sky position of Planet 9 if it is in the region covered by the Dark Energy Survey, and at a brightness accessible to that survey. The European Space Agency's Gaia mission, which is conducting precision astrometry of nearly 2 billion stars, is also relevant to the Planet 9 search, though indirectly. Gaia's precise measurements of stellar positions mean that when Planet 9 is eventually found, its position can be measured with extraordinary precision against the Gaia reference frame. This will accelerate the orbital determination. Additionally, some researchers have proposed searching for Planet 9 using occultation events. If Planet 9 passes in front of a background star, it will briefly block the star's light. The duration of the occultation, combined with the angular size of the star and the distance to Planet 9, can be used to measure Planet 9's diameter directly. Detecting such occultations requires either luck, placing a telescope precisely in the narrow shadow cast on Earth by the distant planet, or a systematic survey of many stars in the predicted position of Planet 9 using a network of small telescopes. This occultation method has been successfully used to study Pluto and Kuiper Belt objects. For Planet 9, the challenge is the uncertainty in its position. With the current orbital uncertainty, the occultation event could occur anywhere along a wide strip of sky, making it impossible to predict when and where to deploy a monitoring network. Once the planet is found and its orbit is better known, occultation prediction will become much more feasible. The combined weight of all these ongoing efforts, Rubin, Subaru, archival searches in existing data, future occultation monitoring, represents an unprecedented investment in the search for a single solar system object. The scientific community has taken the Planet 9 hypothesis seriously enough to devote substantial telescope time and resources to testing it. This level of investment is itself a statement about the strength of the underlying evidence. Astronomers do not organize multi-telescope international searches for objects they consider unlikely to exist. The search for Planet 9 reflects a genuine consensus that the gravitational evidence is compelling enough to justify the effort. The window of 2025 to 2030 is not arbitrary. It corresponds to the period when the Vera-Rubin Observatory will have accumulated enough data to either find Planet 9 or place strong enough upper limits on its brightness to significantly constrain the hypothesis. By 2030, we will almost certainly know whether Planet 9 exists at the parameters currently predicted. That is an unusual situation in astronomy, a specific quantitative prediction with a specific near-term window for resolution. The universe will give us an answer, and we will not have to wait long. The Vera C. Rubin Observatory is under construction on Cerro Pachon in northern Chile at an elevation of about 2,715 meters. When it begins its main science program, the Legacy Survey of Space and Time, it will be the most powerful wide-field optical survey telescope ever built. The Rubin Observatory's primary mirror is 8.4 meters in diameter. Its camera, the world's largest digital camera ever built for astronomy, contains 3.2 billion pixels arranged in an array that covers a circular field of view roughly 3.5 degrees across. For comparison, the full moon is about 0.5 degrees across in the sky. Each Rubin image covers an area of sky 49 times larger than the full moon. The survey strategy for the Legacy Survey of Space and Time is designed to cover the entire accessible southern sky every few nights for 10 years. The survey will return to each point on the sky many hundreds of times over its operational life. Each visit produces an image that, combined with all previous images of the same region, builds up a deep co-added image that reaches stars and galaxies far too faint for any single exposure to detect. What does this mean for Planet 9? At the expected apparent magnitude of 22 to 25, Planet 9 would be detectable in a single Rubin image, or at most in a few co-added images. The telescope is deep enough. The question is the combination of cadence and the moving object detection algorithm. Finding Planet 9 in Rubin data requires identifying a faint object that moves very slowly across the sky over months to years. The standard algorithms for finding moving solar system objects are designed for objects that move significantly during a single night or between images separated by days. Planet 9 moves perhaps 0.01 arcseconds per night. That is much less than the typical resolution of ground-based astronomical images, which are blurred by atmospheric seeing to perhaps 0.5 to 1 arcsecond. In other words, Planet 9 would appear as a stationary point of light in any single image or pair of images separated by days or even weeks. It would move noticeably only over months. Identifying it as a moving object against a background of thousands of faint stationary stars requires comparing images from different epochs separated by months, measuring the positions of every faint object in both images to high precision, and identifying the ones that have moved consistently. This is exactly the kind of analysis that the Rubin Observatory's data reduction pipeline is being designed to perform. The pipeline includes dedicated software for detecting slow-moving solar system objects, including very distant ones. The expected performance of this software, based on simulations and tests with existing survey data, suggests that Rubin will be capable of detecting objects at Planet 9's expected magnitude and apparent motion rate within the first few years of its survey. several research groups have already conducted pathfinder searches using existing telescopes and survey data to test the detection algorithms and constrain the search space. The Dark Energy Survey, using the dark energy camera on the Cerro Tololo Inter-American Observatory, has covered a substantial fraction of the southern sky to depths relevant for Planet 9. Teams from this survey have conducted detailed searches for Planet 9 in the accumulated data without finding it. This either means Planet 9 is not in the region of sky covered by the Dark Energy Survey, or it is there but below the survey's detection threshold. Japan's Subaru telescope on Mauna Kea in Hawaii has also been conducting dedicated Planet 9 searches using the Hypersuprime Cam, a wide-field imager with exceptional sensitivity. The Hypersuprime Cam surveys have reached some of the deepest limits yet achieved for slow-moving outer solar system objects. They have not found Planet 9, but they have placed stronger constraints on where it can be within the region surveyed. The Vera Rubin Observatory is expected to complete its commissioning and begin its main survey in late 2024 or 2025. The first full year of survey operations will cover the entire southern sky, accessible from Chile, which includes a significant portion of the predicted Planet 9 search region. If Planet 9 is in the southern sky and at a brightness within Rubin's detection capability, the telescope should find it within the first 2 to 4 years of operation. This is a genuine prediction. Many of the researchers working on the Planet 9 hypothesis expect that if the planet exists at the parameters they have estimated, the Rubin Observatory will find it within its first few years of full-scale operation. The detection, when it happens, will look like this. An automated detection algorithm will flag a faint point source that has moved slightly between images taken months apart. The movement will be consistent with a distant solar system object on a long-period orbit. The astrometry will be measured across multiple images and combined into an initial orbit estimate. The initial orbit will suggest a semi-major axis of several hundred astronomical units, consistent with Planet 9. Then the follow-up observations will begin. Images from other large telescopes will be taken, confirming the object and measuring its position with improved precision. The orbital arc will lengthen, refining the orbital parameters. Within months, the rough orbital parameters will be confirmed, a planet-sized object at several hundred astronomical units on an eccentric orbit tilted to the ecliptic, with properties consistent with the Planet 9 hypothesis. The discovery announcement will be one of the most significant astronomical announcements in generations, and it will be followed immediately by a different kind of scientific work, determining where exactly the planet is in its orbit, how large it is, whether it has moons, and most importantly, trying to understand where it came from. That last question may matter more than the discovery itself. The NICE model and its successors represent the best current understanding of how the solar system reached its current configuration, and understanding where Planet 9 fits into this story, or fails to fit, requires understanding what the NICE model actually describes. The core of the NICE model is a period of orbital instability that occurred in the early solar system, roughly 600 to 700 million years after the solar system formed. In this model, Jupiter, Saturn, Uranus, and Neptune initially formed in a more compact configuration than they currently occupy, all closer to the Sun and in more nearly circular orbits. Over hundreds of millions of years, gravitational interactions between the planets gradually altered their orbits until a specific orbital resonance was reached between Jupiter and Saturn. This resonance triggered a rapid rearrangement of all 4 giant planets, during which their orbits became more eccentric and expanded to roughly their current sizes. During this rearrangement, the giant planets scattered enormous numbers of smaller objects throughout the solar system. Planetesimals that had been peacefully orbiting in the region beyond Neptune were flung into the inner solar system, creating the late heavy bombardment. Others were scattered into the Oort cloud. Some were ejected from the solar system entirely. The Kuiper belt was sculpted into its current structure by this process. A key prediction of the NICE model is that the giant planet instability should have scattered a significant number of large objects outward, not just small planetesimals, but potentially planet-sized bodies that did not quite escape the solar system. The fate of such a body would depend on the details of its encounter with the giant planets. If it interacted closely with Jupiter or Saturn, it would likely be ejected entirely. If it interacted more gently, or interacted with Uranus or Neptune rather than the gas giants, it might be placed on a distant eccentric orbit. This is precisely the scenario that would produce Planet 9 in the scattering origin story. The NICE model's giant planet instability naturally creates the gravitational environment in which a protoplanet of 5 to 10 Earth masses could be scattered into a distant orbit. The problem is that N-body simulations of the NICE model instability, while they do scatter objects outward, tend to scatter them into very eccentric orbits that either lead to eventual ejection or eventually circularize at distances too large to be consistent with the Planet 9 constraints. Getting a scattered body into an orbit with a semi-major axis of 500 astronomical units and an eccentricity of 0.35 requires a specific sequence of gravitational interactions that the simulations do not produce with high probability. This does not mean the scattering origin is impossible. N-body simulations are statistical. Even a low probability outcome occurs in some fraction of simulations, and the solar system is a single realization of the planet formation process, not an average over many realizations. It is entirely possible that our solar system happened to produce the specific configuration of scattering events that would place Planet 9 in its current orbit, even if this outcome is rare in simulations. The capture hypothesis, conversely, does not require any modification of the standard NICE model timeline. Stellar captures can occur during the cluster phase, which precedes the NICE model instability by hundreds of millions of years. A planet captured during the cluster phase would have been in its current distant orbit long before the NICE model instability rearranged the inner solar system. The stability of Planet 9's orbit over 4.5 billion years, including surviving the NICE model instability without being perturbed into a different orbit, would need to be verified for this scenario, but the orbital constraints suggest it is possible. The most consequential aspect of the origin story debate is what it implies about the early history of the solar system, and whether that history was typical or unusual. Our current models of planet formation predict that solar-type stars should commonly form systems with multiple super-Earths in the habitable zone or close to it. These super-Earth systems are common in exoplanet surveys, but our solar system has no super-Earth in the habitable zone. The inner solar system has Venus and Earth, both slightly less massive than a super-Earth by the most common definition, and Mars, which is much smaller, no super-Earth. One hypothesis for why our solar system lacks inner super-Earths is called the Grand Tack hypothesis, which proposes that Jupiter migrated inward during the early solar system, passing through the region where super-Earths would have formed and sweeping it clean of the material that would have built them. The Jupiter Grand Tack then reversed direction, with Saturn's gravity pulling Jupiter back out to roughly its current position. If Planet 9 is a super-Earth that was scattered outward rather than never forming, it would mean the super-Earth material was present in our solar system, but ended up in a different place than in most other planetary systems. Our solar system would not be lacking a super-Earth, it would have one at an unusual location. This interpretation connects the Planet 9 origin story to one of the deepest questions in exoplanet science. Why do some planetary systems form inner super-Earths and others do not? If the difference is partly a matter of where the super-Earth ends up rather than whether it forms at all, then our solar system and the systems with inner super-Earths might be more similar in their formation histories than their current configurations suggest. This is why the discovery of Planet 9 and the determination of its origin story matters far beyond the specific question of what is in our outer solar system. It would be a constraint on the demographics of planetary systems throughout the galaxy, a data point in the larger story of how common or unusual our solar system is in the cosmic context. Where did Planet 9 come from? This is the question that transforms Planet 9 from an interesting discovery into a paradigm-shaking one. Because the answer, whatever it turns out to be, will require revising our understanding of how planetary systems form and evolve. Every proposed origin story for Planet 9 breaks something in our current models, and the specific something that breaks depends on which origin story is correct. The current standard model of solar system formation is called the Nice model, named after the city in France where the researchers who developed it were based. The Nice model describes how the solar system evolved from a disk of gas and dust surrounding the young sun about 4.5 billion years ago, through the formation of planetesimals and protoplanets, through the formation of the four giant planets Jupiter, Saturn, Uranus and Neptune, through a period of orbital instability that scattered those planets into roughly their current positions, and into the stable configuration we observe today. The Nice model is a triumph of modern planetary science. It explains the orbital structure of the asteroid belt. It explains the Trojan asteroids that co-orbit with Jupiter. It explains the late heavy bombardment, the period of intense asteroid and comet impacts on the early moon and inner planets that occurred roughly 3.9 billion years ago. It makes predictions that have been tested against multiple independent data sets and confirmed in most cases. But the NICE model has no clear place for Planet 9. 3 possible origin stories have been proposed. Each one breaks a different aspect of the standard model. The first is that Planet 9 formed in the inner solar system, in the region where the gas giants formed, and was then ejected into the outer solar system through gravitational interactions with Jupiter or Saturn. During the period of giant planet formation, the gravity of Jupiter and Saturn was flinging objects throughout the solar system. Most of the planetesimals that encountered these giants were scattered inward, toward the Sun, or outward, into the Oort cloud or beyond. Some were ejected from the solar system entirely. It is possible that a protoplanet of 5 to 10 Earth masses encountered Jupiter or Saturn during this period and was scattered outward into an enormous elliptical orbit. This is the most straightforward origin story. It requires no additional unusual events beyond what the standard model already predicts. The NICE model allows for close encounters between the forming giant planets and smaller bodies. A body of Planet 9's estimated mass would have been large enough to survive the gravitational interaction and could have been scattered into a distant orbit rather than ejected entirely. But there is a problem. The scattering mechanism that would send a protoplanet outward to hundreds of astronomical units typically sends it to very large, highly eccentric orbits that would then be circularized by the gravitational tide of the galaxy or perturbed by passing stars. Getting a scattered protoplanet into a stable orbit at the parameters proposed for Planet 9, rather than into an orbit that is too eccentric to be stable or into the Oort cloud, requires specific conditions during the scattering event and the subsequent orbital evolution. It is possible, but the probability of landing on exactly the right orbit is not high. The second origin story is that Planet 9 was captured from another star. The Sun formed in a star cluster, a group of hundreds to thousands of stars that were born together from the same molecular cloud. These clusters typically disperse over tens to hundreds of millions of years as the member stars drift apart. During the period when the cluster was dense, the stars were close enough together for gravitational encounters to be frequent. In some of these encounters, a planet orbiting one star could be exchanged to orbit another star. This is a known mechanism. The capture of objects from other stellar systems has been confirmed in our own solar system for interstellar visitors, like Oumuamua and Borisov, though those were not gravitationally captured. But planet exchange during stellar cluster encounters is a theoretically well-studied process, and it could in principle have transferred a planet from another star system to an orbit around our Sun during the first few 100 million years of the solar system. The capture hypothesis has an attractive feature. It explains naturally why Planet 9's orbit, with a period of 10,000 to 20,000 years and a significant inclination to the ecliptic, does not look like the orbits of the other planets, which are all in nearly the same plane and on orbits that scale with their formation location in the protoplanetary disk. A captured planet would not necessarily match the orbital plane of the native planets. Its orbit would reflect the geometry of the capture event rather than the angular momentum of the solar protoplanetary disk. The problem with the capture hypothesis is the probability. Detailed simulations of how many planets might be captured during typical stellar cluster encounters suggest that the capture rate is low. Perhaps a few % probability per star that a planet is captured from a neighboring system during the cluster phase. That is not negligible, but it means capture is not the most common outcome of cluster membership. And the specific orbit that Planet 9 appears to have would need to result from a specific geometry of encounter that may be unlikely even among successful capture events. The third hypothesis is perhaps the most interesting from a theoretical standpoint. It is that Planet 9 formed in situ, where it is now, from material in the outer solar system that the standard model says should not have been available in sufficient quantity. The standard model predicts that the density of the protoplanetary disk decreases rapidly with distance from the Sun. Beyond roughly 30 to 50 astronomical units, the disk should have been thin enough that planet formation was too slow to produce a large planet before the disk was dispersed by radiation and stellar winds. A planet 5 to 10 times the mass of Earth at 400 to 800 astronomical units should simply not have been able to form there. But this prediction depends on specific assumptions about the structure of the protoplanetary disk. if the disk extended farther than standard models suggest, or if density enhancement mechanisms such as streaming instability concentrated material at large distances, in situ formation might have been possible. Some recent models of disk structure allow for more material at large distances than older models assumed. This hypothesis has the aesthetic appeal of simplicity. The planet formed where it is. No scattering event required. No capture from another star. Just a planet that formed in a part of the solar system we previously thought was incapable of producing it. The problem is that explaining where the material came from and how it concentrated efficiently enough to form a planet at 400 to 800 astronomical units within the lifetime of the protoplanetary disk requires invoking mechanisms that are not yet confirmed and that the standard model does not include. All three origin stories break something. The scattering story breaks the idea that scattered protoplanets land on specific constrained orbits rather than being ejected or scattered into the Oort cloud. The capture story breaks the assumption that the solar system contains only objects formed in its own protoplanetary disk. The in situ story breaks the assumption that the outer solar system disk was too diffuse for planet formation. The breaking of these ideas would not be unique in the history of planetary science. Every major advance in our understanding of the solar system has required revising some assumption we thought was secure. The discovery of hot Jupiters orbiting other stars very close to their parent stars required revising the assumption that giant planets form far from their stars and stay there. The discovery of the Kuiper belt required revising the assumption that the solar system ended at Neptune. The confirmation of large-scale planetary migration through the Nice model required revising the assumption that the planets formed roughly where they are now. Planet 9, if confirmed, would be another such revision. But it would be a particularly profound one, because the origin story of Planet 9 is not just a local curiosity. It tells us something about whether our solar system's formation was typical or unusual, and whether the models we use to interpret the planetary systems we're finding around other stars are capturing the full range of possible outcomes. The most common type of planet in the galaxy, based on exoplanet surveys, is a super-Earth or mini-Neptune, a planet between Earth's mass and Neptune's mass. These planets orbit other stars in enormous numbers, but our solar system apparently lacks them, at least in the inner and middle solar system. If Planet 9 is a super-Earth hiding in the outer solar system, it would mean our solar system does have a super-Earth, just much farther out than the ones we find around other stars. And it would raise the question of whether some fraction of the super-Earths we see orbiting close to other stars might have started out where Planet 9 is and migrated inward, and whether the absence of super-Earths in our inner solar system was caused by a different dynamical history than what other planetary systems experienced. The origin story of Planet 9 is not just the story of one planet, it is a constraint on how solar systems work. If Planet 9 formed in our protoplanetary disk and was scattered outward, it tells us that the scattering process of giant planet formation regularly produces large planets in distant orbits. This would have implications for interpreting the demographics of exoplanet systems. If Planet 9 was captured from another star, it tells us that stellar birth clusters are efficient at exchanging planets between stars, and that every solar-type star might have a probability of carrying a captured alien world in its outer reaches. There might be billions of such captured planets in the galaxy, orbiting in the distant periphery of stellar systems, invisible and uncounted. If Planet 9 formed in situ at hundreds of astronomical units, it tells us that planet formation in the outer regions of protoplanetary disks is more efficient than we thought, and that distant planet formation might be a standard feature of stellar system evolution rather than the exotic exception. The specific connection between Planet 9's origin story and the demographics of exoplanet systems deserves more attention, because it is where the Planet 9 discovery connects to some of the most active questions in astronomy today. Exoplanet surveys, beginning with the Kepler mission in 2009 and continuing with TESS and ground-based radial velocity programs, have established that the most common type of planet in the galaxy is a planet with a radius between 1.5 and 3.5 Earth radii and a mass of roughly 2 to 10 Earth masses. These planets, the super-Earths and mini-Neptunes, are found orbiting a majority of Sun-like stars. They are so common that if our solar system lacked such a planet, our solar system would be in the minority among planet-hosting stars. Our solar system does not have such a planet in the classical habitable zone or at the distances where most exoplanet super-Earths are found. The absence of a super-Earth in the solar system has been noted as a genuine puzzle, and several explanations have been proposed. The Grand Tack hypothesis, proposed by Kevin Walsh and collaborators in 2011, suggests that Jupiter's early inward migration swept the inner solar system clean of the material that would have formed a super-Earth. In systems where Jupiter does not migrate inward this extensively, the super-Earth material survives and forms one or more large planets in the habitable zone. The empty embryos hypothesis suggests that the lack of a super-Earth in the solar system reflects an unusually low mass of solids in the inner solar system during planet formation, perhaps related to the initial conditions of the protoplanetary disk. The clearing by Saturn hypothesis involves Saturn's influence during the Nice model instability, which might have cleared embryos from the inner system during the orbital rearrangement. All of these hypotheses share the assumption that the solar system simply does not have a super-Earth, that the material that would have formed one was destroyed, scattered, or never present. Planet 9, if confirmed, would challenge this assumption. The solar system might have a super-Earth. It would just be in an unusual location, the outer darkness beyond Neptune rather than in the inner system. This changes the framing of the question. Instead of asking, why doesn't the solar system have a super-Earth? We would need to ask, why does the solar system have a super-Earth at such extreme distances, rather than in the inner system where most exoplanetary super-Earths are found? The two questions have different implications for our understanding of planet formation. The first question implies that the solar system is deficient in something that other systems have. The second implies that the solar system has the same planet type but in an unusual location, suggesting that the process that determines where a super-Earth ends up is different in different systems, not the process that determines whether one forms. This reframing has implications for exoplanet science specifically. If some fraction of planetary systems scatter their super-Earths outward to distant orbits, rather than retaining them at shorter periods, then the exoplanet census is missing a population of distant super-Earths that are not detectable by current radial velocity or transit surveys. The true occurrence rate of super-Earths, the fraction of stars with at least one, might be higher than current surveys suggest. This would be an important correction to the census. Current estimates of the occurrence rate of super-Earths are used in a variety of calculations, from estimates of the number of potentially habitable planets in the galaxy to models of the diversity of planetary system architectures. A correction to the occurrence rate, even a modest one, would propagate through these calculations and change the answers. The Planet 9 discovery, if it occurs, would thus contribute not just a data point to our local solar system inventory, but a new perspective on the statistics of planetary systems throughout the galaxy. That is an unusually broad scientific impact for a single object discovery. The inverse question is also interesting. Given that we know super-Earths are common in exoplanet systems, and given that some fraction of those systems might have their super-Earths in distant orbits rather than close orbits, what fraction of distant super-Earths would be detectable by current means? The answer is almost certainly a very small fraction. A super-Earth at 500 astronomical units, orbiting even a nearby star, would be far beyond the reach of radial velocity measurements, too faint for direct imaging in most cases, and essentially undetectable by transit. We would not know those distant super-Earths were there, just as we have not known Planet 9 was there. The universe may be full of distant, cold, undetected super-Earths, and the first one we find may be right here in our own solar system. Every origin story is consequential. Every one of them reshapes something important. That is the specific weight of the Planet 9 discovery, if it is confirmed. It is not just a new planet in our solar system. It is a new constraint on how the solar system formed, and therefore a new constraint on how planetary systems in general form. The evidence is in the data, the search is narrowing, and the instrument that might finally resolve the question is coming online now. There is a specific irony in the Planet 9 story that is worth dwelling on before the close. The irony is this: we live in an era of unprecedented astronomical capability. We have telescopes in space measuring the cosmic microwave background to fractional microkelvin precision. We have detected gravitational waves from black hole mergers billions of light years away. We have imaged the shadow of a black hole at the center of a distant galaxy, a shadow measuring light years across, from a distance of 55 million light years. We have catalogued the positions and colors and spectra of billions of galaxies. We have characterized the atmospheres of planets orbiting stars dozens of light years from Earth, and we cannot find a planet 5 to 10 times the mass of Earth in our own solar system. The planet is not hiding in some distant galaxy. It is orbiting our own sun. It is part of our solar system. The system we have been studying since Galileo first turned a telescope on Jupiter's moons in 1610. The system whose every known major body has been mapped, measured, and characterized in exquisite detail. And somewhere in that system, probably within 600 astronomical units of the Sun, a planet is sitting in the dark, completing its slow orbit, immune to detection by every instrument we have deployed. This is not a failure of astronomy. It is a lesson in the specific challenges of finding cold, distant objects in the outer solar system. The difficulty is real, and the physics is clear, and the solution is coming online now. But the situation is a useful reminder of the limitations of even the most capable science. We know a lot about the universe. We know almost nothing about our own backyard beyond 50 astronomical units. The Kuiper Belt, the region from 30 to 50 astronomical units, has been surveyed reasonably well. We know its population of objects to an approximate census. But beyond 50 astronomical units, the survey coverage drops off dramatically. The extreme trans-Neptunian objects, the objects that have revealed the Planet 9 signature, number in the dozens among objects with well-determined orbits. There are probably thousands of similar objects we have not found, simply because they are too faint and too slow-moving for current surveys to detect. The outer solar system is, in a very real sense, the last unexplored frontier in our immediate cosmic neighbourhood. Not unexplored in the sense that we have sent no spacecraft there, though that is also largely true beyond the distance of the Voyager probes. Unexplored in the sense that we do not have a complete census of what is there. The Vera Rubin Observatory will change this significantly. In 10 years of operation, it is expected to discover tens of thousands of new solar system objects, including hundreds to thousands of new trans-Neptunian objects. The census of the outer solar system will be transformed from a sparse and incomplete sample to something approaching a complete inventory of objects bright enough for Rubin to detect, and in the course of that inventory, if it is there, Planet 9 will be found. The specific prediction is quantitative. If Planet 9 exists at the parameters consistent with the TNO clustering analysis, the probability of Rubin detecting it within the first 5 years of survey operations is estimated by various groups at between 50 and 90%. Within 10 years, the probability approaches certainty if the planet is in the sky region accessible to Rubin and within the predicted magnitude range. The decade between 2025 and 2035 is the window. It is a narrow window on cosmic timescales, and a long one on human institutional timescales. But it is the window we have, and the instrument that will open it is almost ready. The answer is close, closer than it has ever been. And when it comes, it will be one of the most significant answers in the history of planetary science. This is the state of the Planet 9 question as it stands today. The evidence is real. The orbital clustering of extreme trans-Neptunian objects is measured, not assumed. The statistical significance of the clustering, even accounting for the most generous estimates of observational bias, remains difficult to explain without something doing the gravitational shepherding. The parameters of whatever is responsible for the clustering point consistently toward a planet of 5 to 10 Earth masses at hundreds of astronomical units from the Sun. The counter-evidence is also real. The observational bias in TNO surveys is genuine and significant. The number of known extreme trans-Neptunian objects is still small enough that adding or removing a few from the analysis changes the statistical picture. Some researchers who have examined the data carefully have concluded that the evidence for clustering is weaker than Batygin and Brown's original analysis suggested. The debate within the astronomical community is genuine and ongoing. What is not in dispute is that if Planet 9 exists at the parameters suggested by the best current models, it should be detectable by the Vera Rubin Observatory within the next several years. This is the specific and testable prediction that elevates the Planet 9 hypothesis above the level of pure speculation. A hypothesis that makes predictions that can be tested is a scientific hypothesis. The Rubin Observatory is the test. If the Rubin Observatory conducts its survey through the predicted search region and finds nothing, that result will place strong upper limits on the mass and brightness of any object in the predicted orbital range. It will not definitively rule out Planet 9, because the planet might be outside the survey region or at the faint edge of detectability. But a non-detection by Rubin will significantly weaken the Planet 9 hypothesis and redirect the scientific conversation. If the Rubin Observatory finds an object consistent with Planet 9's predicted parameters, the discovery will be confirmed and the origin question will move to the centre of planetary science for a generation. The specific moment of discovery is worth imagining in detail. An astronomer at a computer terminal, reviewing the output of the automated detection pipeline that is processing a night's Rubin data, will see a flag, a faint point source, magnitude perhaps 23, that the pipeline has identified as a candidate moving object based on comparison with images from months earlier. The motion rate and direction will be consistent with a very distant solar system object. The position will be in the predicted Planet 9 search region. The astronomer will not immediately know what they have found. The candidate will be one of thousands that the pipeline processes, most of which are asteroids or faint background galaxies or cosmic ray hits. But this one will have specific characteristics that make it interesting. The very slow motion rate and the extreme distance implied by that rate. Follow-up observations will be requested. A large telescope, possibly the European Southern Observatory's Very Large Telescope, will image the same region a week later, and then a month later. Each image will confirm the object and refine its position. The orbital arc will lengthen from days to weeks to months. After perhaps 6 months of follow-up, a preliminary orbit will be calculated. Semi-major axis, approximately 500 to 700 astronomical units. Eccentricity, approximately 0.4 to 0.5. Inclination, approximately 20 degrees. The orbital parameters will match the Planet 9 prediction. There will be extraordinary caution. The history of astronomy is littered with premature announcements of major discoveries that did not survive scrutiny. The team will wait until the orbital determination is robust, until the statistics are unambiguous, until multiple independent groups have examined the data and reached the same conclusion. And then the announcement will be made. It will be the first planet discovered in our solar system since Neptune in 1846. The first planet whose existence was predicted from gravitational anomalies before it was seen. The first confirmation that our solar system harbours a category of planet, the super-Earth or mini-Neptune, that is otherwise the most common type in the galaxy, and the beginning of an entirely new chapter in the study of how planets form and where they end up. There is one more thing worth considering. What if it is not found? The Vera Rubin Observatory will cover approximately half the sky to the depth required to detect Planet 9, if it is in the predicted parameter range. If a careful survey of the full predicted search region reveals nothing, the implications are also significant, though less dramatic. A non-detection would not immediately refute the Planet 9 hypothesis. The clustering of extreme trans-Neptunian objects would still require explanation. But it would shift the burden of proof. It would require either a significantly revised Planet 9 hypothesis, with different orbital parameters that put the planet in regions of the sky not covered by the survey, or a different explanation for the TNO clustering. Several alternative explanations for the TNO clustering have been proposed. The most interesting is the self-gravity hypothesis, that the extreme trans-Neptunian objects, if there are enough of them, could collectively generate enough gravitational force to shepherd each other into aligned orbits without any external massive planet. This hypothesis has been worked out in detail and is physically plausible, though it requires a much larger population of TNOs than currently known, and their collective mass would have to be significantly larger than what current surveys suggest. There is also the possibility that the clustering is partly explained by the galactic tide, the differential gravitational pull of the galaxy's mass on solar system objects at large distances. The galactic tide is a known force that shapes the orbits of Oort cloud comets, and might also affect the very distant TNOs. Some researchers have suggested that galactic tide effects, combined with observational bias, might explain a portion of the observed clustering without requiring a large planet. These alternatives are worth taking seriously. They remind us that the Planet 9 hypothesis, however compelling, is a hypothesis. The evidence is strong but not conclusive. The prediction is specific and testable. The test is coming. Whether the test confirms or refutes the result will be significant. That is all we can ask of science, clear questions with testable answers. The Rubin Observatory is the instrument. The next few years are the window, and the universe, as always, has already decided what is out there. We are simply waiting to find out what it decided. In the meantime, there are billions of miles of dark cold space between Neptune and whatever comes next. And in that dark, moving slowly on its enormous elliptical path, carrying the gravitational signature that 12 distant small worlds have been patiently broadcasting for billions of years. Something is out there. We mapped the evidence, we mapped the search, and the physics of why it hides is not a mystery, but a precise description of what we are looking for. Something large, cold, distant, patient, 4.5 billion years of orbits completed in silence, and maybe, in a few years, found. The thermal emission story has one more layer that is worth adding, because it connects to a potential future detection strategy that is not optical at all. The Atacama Large Millimeter Array, known as ALMA, is an array of radio antennas in the Chilean Atacama Desert, operating at millimeter and submillimeter wavelengths. These wavelengths correspond to frequencies between roughly 30 and 950 GHz. A 40 Kelvin object emits a significant fraction of its thermal energy at millimeter wavelengths. The Wien displacement law puts the peak emission at about 70 micrometers, but the blackbody spectrum extends to longer wavelengths with significant power. At millimeter wavelengths, the atmosphere is more transparent than at far infrared wavelengths, particularly at the very dry high-altitude site of the Atacama. ALMA can observe at these wavelengths with high sensitivity and excellent angular resolution. The sensitivity of ALMA for a 40 Kelvin point source at 600 astronomical units is marginal at best, but ALMA's sensitivity has been improving with each expansion of the array and each improvement in receiver technology. Some researchers have estimated that a targeted ALMA observation of a specific sky position, knowing where to point based on optical prediscovery, could detect Planet 9's thermal emission in a relatively short integration time. This matters for two reasons. First, if Planet 9 is found optically but is near the Rubin detection threshold, confirmation through an independent detection at a different wavelength would significantly strengthen the discovery announcement. Second, a thermal detection would allow a direct measurement of the planet's size, since the thermal emission is proportional to the planet's surface area and temperature, and the temperature is known from the equilibrium calculation. An optical detection gives the planet's reflectivity and position but not its size directly. A thermal detection gives size and temperature. The combination of optical and thermal measurements would allow calculation of the planet's albedo, the fraction of incoming sunlight that it reflects. Albedo is an important diagnostic for the composition of a solar system object. High albedo indicates icy surface material. Low albedo indicates darker rocky or organic material. Knowing Planet 9's albedo would provide the first direct clue about what it is made of. There is also the possibility of detection at radio wavelengths. If Planet 9 has a magnetic field and a magnetosphere, it may emit cyclotron radiation at radio wavelengths, as Jupiter and Saturn do. Jupiter's radio emissions are detectable at Earth and have been studied in detail. At 600 astronomical units, Jupiter's radio emissions would be far too faint to detect with current radio telescopes. But Planet 9, at 5 to 10 Earth masses, might have a magnetic field significantly stronger than Jupiter's, and if it does, and if its magnetosphere is active, the radio emission might be detectable with future radio arrays. This is speculative. We do not know whether Planet 9 has a magnetic field, but it is another potential detection pathway that illustrates the richness of the observational possibilities once the planet's position is known. The multi-wavelength picture of Planet 9, combining optical, near-infrared, far-infrared, millimeter, and possibly radio observations, would provide a characterization of the planet that exceeds our knowledge of any comparable solar system object discovered before the space age. We have better tools now than Herschel had when he discovered Uranus or Galahad when he confirmed Neptune. We can learn more from the first detection than any previous planet discovery allowed. The challenge is getting to the first detection. Everything else follows from that. The constraint from the Cassini spacecraft ranging data deserves more detailed discussion because it illustrates an unusual aspect of how Planet 9's existence is being constrained, indirectly, through its gravitational influence on objects whose orbits we can measure with extraordinary precision. The Cassini spacecraft orbited Saturn from 2004 to 2017. During that 13-year period, the mission regularly transmitted radio signals to Earth and received signals back. By measuring the round-trip travel time of these signals with high precision, scientists could determine Cassini's position relative to Earth with centimeter-level accuracy. Knowing Cassini's position means knowing Saturn's position, because Cassini's orbit around Saturn is well characterized. Over 13 years, scientists built up an extraordinarily precise record of Saturn's orbital position as a function of time. If a massive distant planet exists, its gravity should produce a small but measurable perturbation in Saturn's orbit. The perturbation is small because Planet 9 is far from Saturn, and its gravitational influence decreases with distance. But the precision of the Cassini ranging data is high enough that even a small perturbation should be detectable if it is real. The analysis by Fienga and collaborators found that the Cassini ranging data is consistent with no perturbation from Planet 9 for most orbital positions of the hypothetical planet. But for specific positions of Planet 9 in its orbit, the expected perturbation would have been detectable and is not seen, placing those positions in the excluded zone. The result maps out a pattern of allowed and excluded regions in the predicted Planet 9 parameter space. The excluded regions are those where Planet 9 would currently be positioned close enough to Saturn in the plane of the ecliptic to produce an angular perturbation larger than the Cassini measurement uncertainty. The allowed regions are those where the perturbation would be below the measurement threshold. This analysis is independent of the TNO clustering evidence. It uses completely different data and completely different methodology. The fact that the two independent lines of evidence, the gravitational shepherding of TNOs and the non-perturbation of Saturn's orbit, are consistent with the same range of Planet 9 parameters is a meaningful cross-check. It is not a detection. It is a constraint. But it is a constraint from an independent method, and consistency between independent methods increases confidence in the overall picture. The Cassini constraint also has practical implications for the search. The excluded regions defined by the Cassini analysis can be deprioritized in the optical search. If Planet 9's current position is most likely in the allowed regions, focusing the search on those regions first maximizes the probability of detection per unit of telescope time. This kind of multi-method triangulation using independent datasets to narrow down the search parameter space is exactly how modern astronomy solves hard detection problems. No single measurement is definitive, but the combination of multiple consistent constraints closes in on the answer. Planet 9's existence is being constrained from multiple directions simultaneously. The TNO, orbital clustering, the Saturn ranging data, the non-detection in WISE infrared surveys, the non-detection in dark energy survey optical data, the non-detection in Subaru hyper-suprime-cam searches. Each non-detection in a surveyed region narrows the allowed parameter space. Each new TNO discovered with the right orbital properties strengthens the clustering signal. The parameter space is closing in. The object being described by all of these constraints is becoming more precisely defined with every new dataset. Whether the object is real or an artifact of incomplete data will be answered by the Rubin Observatory. The countdown has begun. There is one more thread to follow before closing the mission briefing, and it concerns not the planet itself but the implications of its discovery for a question that touches on something more personal than planetary science. If Planet 9 exists, and if it has existed in its current orbit for most of the 4.5 billion year history of the solar system, then it has been present throughout the entire history of life on Earth. It has been silently completing its slow orbit, while single-celled organisms evolved into multicellular life in the Proterozoic oceans, while the Cambrian explosion generated the basic body plans of all complex animals, while the dinosaurs rose and fell, while hominids evolved on the African savanna, while humans built the first cities and developed writing and mathematics and astronomy. For all of that time, for all of human history and all of the history of life, a planet 5 to 10 times the mass of Earth has been orbiting our star. We have been in the same solar system as Planet 9 since the moment the solar system formed. We have shared this gravitational neighborhood for 4.5 billion years, and we did not know. This is not unusual in astronomy. We did not know Uranus existed until 1781, and it is visible to the naked eye under good conditions. We did not know Neptune existed until 1846. We did not know about the Kuiper Belt until 1992. We did not know about the vastness of the Oort cloud until theoretical arguments pointed to it in the mid-20th century. The history of astronomy is largely a history of discovering things that were there all along. But there is something specific about Planet 9 that makes its potential discovery feel different from these previous additions to the solar system inventory. Planet 9 would not just be a new object in the catalogue, it would be a reclassification of the solar system itself. We thought we knew how many planets our star had. we would turn out to be wrong by at least one, and possibly by more if the dynamic processes that produce Planet 9's orbit also scattered other large bodies into distant, undetected orbits. The discovery would also reopen the question, briefly raised and then largely set aside after Pluto's reclassification, of what a planet actually is and how to define the boundaries of the solar system's planet inventory. Planet 9 at 500 astronomical units is far from the traditional boundary of the classical solar system, which is usually drawn at Neptune's orbit around 30 astronomical units. Is an object at 500 astronomical units part of the solar system? In what sense? What is the outer boundary of our planetary system? These questions are not merely semantic. They reflect genuine uncertainty about the structure of the outer solar system and about what gravitational processes have shaped it. The answer to where the solar system ends, if there is an answer, is connected to questions about what Planet 9's orbit implies about the history of the outer solar system and about the extent of the Sun's gravitational influence. The outer boundary of the solar system is not a sharp line. It is a transition zone from the region where the Sun's gravity dominates all dynamical processes to the region where the galactic tide and stellar encounters compete with and eventually dominate the Sun's gravity. In the Oort cloud, the Sun's gravity and the galactic tide are comparable in influence. In the inner Oort cloud, the Sun's gravity still dominates, but galactic tides are significant. In the classical Kuiper belt and inner solar system, the Sun's gravity is essentially the only gravitational force that matters. Planet 9 at 500 astronomical units sits in a region where the Sun's gravity is still the dominant force, but where galactic tides and stellar encounters have played a significant role in shaping orbits over the age of the solar system. It is in the transition zone between the well-understood classical solar system and the poorly understood outer reaches where our models are most uncertain. Finding Planet 9 would help calibrate our models of this transition zone. It would give us a specific constraint on the orbital evolution of objects in the 100 to 1000 astronomical units range, a range that is currently the least well-characterized region of the solar system, and it would begin the process of building a complete picture of the entire extent of our solar system, from Mercury at 0.4 astronomical units to whatever is at the outer edge of the Oort cloud at perhaps 100,000 astronomical units. We are planetary detectives, tracing a gravitational fingerprint through the orbits of small worlds we barely know exist. The evidence is strong. The prediction is specific, the instrument is coming online. We are close, and there is one specific number that puts the entire search in perspective and which deserves to be the final thought before this mission briefing closes. The Vera Rubin Observatory will image the entire accessible southern sky roughly every 3 nights for 10 years. In that 10-year period, it will collect more optical data about the sky than all previous surveys combined. The total data volume will be approximately 60 petabytes. Every point in the southern sky will have been imaged hundreds of times, at different wavelengths, at different phases of the moon, in different seasons. Within that 60 petabytes, if Planet 9 exists at the parameters suggested by the gravitational evidence, are the images of it. Not theoretical images, actual images. Photons from Planet 9 that have already been reflected from its surface and are even now travelling toward Earth at the speed of light will be arriving at the Rubin Observatory's mirror over the next few years. They will be recorded in the camera. They will be stored in the data archive. The detection of Planet 9 will consist of recognizing in that enormous sea of data a faint point source that moves very slightly from one epoch to the next. The data already contains the planet if it exists. The challenge is finding it in the noise. This is the specific character of modern astronomy's frontier discoveries. They are not made by pointing a telescope at a dark patch of sky and waiting for something new to appear. They are made by analyzing enormous volumes of data, looking for subtle signals buried in the noise, using algorithms designed to find exactly the kind of signal expected. Planet 9, if it is there, is already in the Rubin data. We just have not processed it yet. That is the state of the search. That is where we are in the mission briefing. The planet may already be found, in the most technical sense, in a file on a server in Chile, waiting for the right algorithm to identify it. The discovery might happen tomorrow. It might happen in 2027. It might not happen at all if the planet does not exist or if it is outside the survey region or below the detection threshold. But the search is the most serious and most capable that has ever been conducted for an unconfirmed solar system planet, and the window is open. Strap in, keep looking outward, and stay with the crew. If you want more mission briefings like this, subscribe for the next journey.